everyone, this is PrachiGupta. This is our new collab. I'm going to present you about the TensorFlow operations. So let's begin. It will contain all these sections. Let's start with the first section. Here we are installing the libraries. I have already installed the libraries. Moving forward, I'll just pause the video. Once the installation is done, we will continue. Okay, so installation is done. Now I'll just proceed ahead. So here we are importing the TensorFlow file, numpy, whatever libraries are required, we are importing it, and we are printing the versions. I'll just run it. We can see the versions. After that, first let's introduce with the tensors. What are tensors? Tensors are generally multi-dimensional array to generalize scalars, vectors, matrices for higher dimension. Uh, it can be 2D, 3D, 1D, any dimensionality matrix. 1D, 0D is known as scalar, 1D is known as vector, 2D is known as matrix, 3D is known as tensor. Why tensors? Because images and videos and all those things are very high dimensionality data which we want to represent. That's why we use tensors. So let's move ahead. I have this scalar. So let's start from Python list. So I have defined a single element in the tensor, TF. TF is the TensorFlow library that we have installed. So from TF dot constant we have defined a scalar, and we will print the value, shape, and the dimension. So it was single value, so it was zero dimensionality. Now we are passing a one dimensional tensor, that is a list. Once we will run it, we will see the shape and the dimensionality is 1. Similarly, we will do for matrix. It will give the matrix and it will give the dimensionality 2. Here we are passing the 3-dimensional list, so we can see the dimensionality is coming as 3. Moving ahead, we have this visualize tensor shapes function that we have created to visualize the tensor. So I'll just run it first. I'll show you the output, then we will go through the code how it's happening. So you can see in the output for 1D we have one single element. For 1D we have this one single list. For 0D we have single element. For 2D we have this matrix, and for 3D tensors we have this structure. So let's move ahead. Let's see how we have done is for scalar we have just directly plotted a box. For vector we have plotted the axis in a rectangular plot, and then we have given the colors and all those details. For matrix again we have done plot rectangle, and then we have given the details. For 3D, here we are plotting the 3D tensor, and we are passing the details. So this is how we are, and then we are calling this function to plot it. Moving forward, now we have to see some special tensors. So sometimes we need a specific tensor, like a matrix containing all zeros, all ones, or any particular number. So for that we use these functions. tf.0 defines the zeroth tensor, tf.1 used to define matrix with all ones, and tf.fill defines the matrix of the same value that you are passing. So suppose here you are passing 2 comma 2 and 7.0, so it will create a matrix of 2.2 with 7.0 all element. So this is how it works. Let's move forward. Identity matrix. So in identity matrix the diagonal is 1 and rest are 0. And diagonal matrix, you can give the diagonal what values you want to give in the diagonal, and it will create a diagonal matrix for you. So this is how this special matrix works. Let's move forward. We have this sequential values and line space. So here you give the range. So range will be start, stop, and the step. So it will start from 2 till 10 and take a step of 2, so 0, 2, 4, 6, 8. For line space it will be like evenly spread values from 0 to 1, and there will be total 5 values. So this is how it is used, tf dot line space and tf dot range. Now if we want some random tensors, which is very important for our neural network, what we will do, we will do tf dot random dot uniform. We can create three different type of random tensors: random uniform, random normal, and random truncated normal. So we can see the difference between them in the output. So this is a random uniform tensor. This is a random normal. It will be, so normal tensor will be normally distributed data, and it is a truncated normal. So this is how normal, but the values are greater than 2 pi. So moving ahead to deep learning weight initialization patterns. So let's see how do we do it. So here we are just printing the title. We'll move ahead. So for the weight initializations, we are defining n in and n out. Basically, with it is the f in and f out dimensions that we are defining for our neural network. 7484 will be the f in and 256 will be the f out. Moving forward to the Xavier standard deviation, it's the defined formula for calculating the Xavier's standard deviation. It will help us to calculate the spread out. Once we have calculated this, we will create a normalized distribution using the f in and f out and the standard deviation what we have calculated from here. Once that is done, we will do he initialization using this formula, and we will print the value and the shape. Once that is done, we'll print the details. So I'll just run it. So here we are initializing the details. Once that is done, we will visualize the frequency, the width value, and the he initialization with respect to he initialization, Kira's Gloroth uniform, and then Xavier's standard deviation that we have calculated. So we will plot the graphs to understand. So see, these are the graphs which gives us this. So we had one normal frequency distribution. It is for the Xavier, and we can see how the Kira's cloth uniform is different from this. So moving forward to tensor data types, we have to be very careful while choosing the data type, because the if we don't choose the right type of data, it will affect the memory, the computation speed, as well as the numeric precision. So moving forward, we have this types of data types. Um, Total in the tensor, and we are printing those data types here. So this is float, half precision, double. Default neural network is float 32. All these examples are here, and this is the use case of that particular type. Moving to the next is typecasting, converting between two types. We can easily convert one type to another type using as int or as float uh, type conversions. So we have defined one constant, and then we want to change it to first we will print the default type, then we will change it to as int, and then we will give the print, and then we will print it to as float. Let's see how it actually works. So see, it converted to int, it truncated the float to integers, and then again it changed it to float. So this is how it works. Moving toward the next cell is memory uses comparison. So I'll just run this code first. We have defined 1 million elements shape, and we want to see how much tensor will take. uh, so basically we are defining tensor of one common shape, and we will define different data types for that tensor, and we will see how memory effect changes. So we are calculating the bytes per unit, and then we are doing the total, and we are printing the total memory it will require. So if you can see, float 16, a tensor shape of 100 1 million elements, If we define it by float 16, it will take this much memory. If we define it with the float 64, it will take this much memory. So like that. Now moving forward to tensor attributes. There are different attributes that will be helpful for us in future during our deep learning. So that we will use constantly is shape, will give the shape of dimensions of the tensor shape. It will give the number of dimensions. It will give the n dimension will give you the number of dimensions. The d type will give you the data type, and dot device will give you where the tensor lives, in which device. So we will run this and we will see how we get output. So suppose we have this normal tensor, and then if we do the shape, it will give us the shape, dimensionalities, the type, and the device. Like this it works. So moving forward to converting TensorFlow to NumPy Python. So how can we convert between all those things? So here we are doing conversions. So first we have defined a TensorFlow, and we are doing tensor.numpy. So we are basically transforming this tensor to numpy. So this is how we change it to numpy. Now how we change our numpy to tensor? So we will go tf dot constant and we will give our pass our numpy. So it will transform our numpy to the tensor. Similarly, it works with dot convert to tensor also. We can pass just our numpy and it will convert it to the tensor. So I'll just run it. We can see the output. It is converted. So this is how it looks. Here we have scalar to Python as well. We just have to give tf constant and the scalar. So it will automatically convert it to the Python. So this is how the conversions work here. Moving forward to TensorFlow operations work on NumPy. So this is basically TensorFlow functions automatically convert NumPy arrays. So suppose we have this NumPy, and we are applying this NumPy array, and we are applying this TensorFlow operation or TensorFlow function, and we have given the NumPy arrays input. So it will automatically convert it while producing the output. Suppose we have this constant TensorFlow defined, and if we add a TensorFlow to a NumPy array, it will automatically combine it, change it, and combine it. It won't give us a array. So this is handled automatically. Now next part is indexing and slicing. So indexing, we have already discussed in C2 file. The video is already uploaded on the channel. I'll share the link. So this is the C3 part. So we will move forward and we'll skip the indexing part. Slicing, indexing, slicing, all these things we have discussed in C2. The boolean masking thing also discussed. Reshaping we have already discussed in C2. So this all thing, transposing, squeezing, unsqueezing, all these things we are concatenating, stacking. These all things we have already discussed in C2. So you can go there. Arithmetic operations again we have seen in C2. So I'll just move forward. Activation functions we have already discussed: sigmoid, 10h, ReLU, leaky ReLU. All these are already discussed. We have seen the code of this in the uh, C2. All the operations work similarly. All the squeezing, unsqueezing, only difference will be there in some format or something, but the main logic behind working of these things are similar. See, we are passing this element, we are masking it to true false. We are normally slicing the elements, indexing it, everything, all the logic is same. So you can just go through C2, and if you will run these codes, you'll automatically understand what is happening here. So that's why we are skipping it. You will go through C2, you will understand it. Mathematical operations all we have done there as well, and it's similar to them, no changes. mm, we can move forward with this as well. Trigonometric we have seen. Broadcasting also we have seen, it's same. what we have in the C is seen in the C2, the same code is here. So I'm skipping this part. Matrix multiplication we have already seen. uh, Matrix decomposition we have already seen there. Einstein summation we have already discussed there. We have discussed there, and we have also seen, let me just parallelly open it. So this is the C2 file. I have opened it, and you can see in this C2 file we have everything. We have this and some operations also. We have performed all this. We have seen all these things in deep learning. We have gone through this cheat sheet, how to use them, all the operations on INSUM we have already discussed in C2. That's why I'm skipping this part in C3. You can go to the video of C2 and you will get to know it there. The whole function, everything is same there. So I'll just skip this part. Broadcasting rules again we have discussed there. Linear algebra, matrix multiplication, the core of neural network we have already discussed it there. Let me open again, I'll show you where we have done this matrix multiplication. So here we have matrix multiplication. We have seen, see, this is matrix multiplication. We have seen it already here, that's why I'm skipping this part. And I have already explained it in the C2 video, that's why I'm skipping this part. Einstein summation we have seen. The same cheat sheet that we saw in the C2, it's the same cheat sheet. This. So let's move ahead. This all we have seen. Okay, let's move to the common deep learning patterns. So in this common deep learning patterns we have dense layer, uh, which is a fully connected layer. So a simple dense layer or fully connected layer, we have this X as a input tensor, W is the weight matrix, B is the bias vector, and A is the activation function, and it returns the batch tensor batch size and the output feature. So this is the linear formula that we do for dense layers, and to apply the activation function we do it like this. And this is the example. We are defining a batch size, input dimension, output dimension. We have defined a x, b and w here, some random normal x and w, and then we have defined a b of all zeros, and we are printing all these things, and once we printing we will call this dense layer and the activation function as ReLU, and then we will see how the output looks. So this is how it is looking. We have given this as input and this is our output. We passed these details to the dense layer and it processed and gave us this output. Now the next is softmax and the cross entropy loss. So let's suppose this is our one of the class, and this is another class that we have created. So these are all our raw scores, and this one is a hot encoded. So once we print it, we'll see the true labels also, the hot encoded. Then how do we implement softmax? So we'll define the function where we will basically what is happening here is this code for the softmax and the cost entropy is used for classification. This code demonstrates the standard way a neural network turns the raw numbers into a final classification and measures how wrong the prediction is. So here's the step by step logic, how we do it. First we logis are the raw scores from the final layer. this logist with that we are defining are the raw scores from the final layer of our model. And notice that the first row 2.0, 1.0 and 0.1, the highest score is at index 0. So that means the this model thinks the input belongs to class 0. So then we will move forward. Since the raw scores can be anything, we use the softmax max is to squeeze them into probabilities that sums to 0. So that's what we do in the softmax. So we'll squeeze them to here we are doing. So we will squeeze them into the probabilities such that their sums will be 0. Once that is done, the next step will come the cross entropy step. So in the cross entropy step, it measures the distance between the model's probabilities and the label, the truth. So the logic is, if the model is very confident in the correct class, the loss is low. If the confident is in the wrong class, then the loss is high. So the maths we use here is sum of labels cross tf dot maths log of probabilities and the epsilon. So this is how we calculate the cross entropy. And why we use it is, uh, uh, we can, at the bottom, if see if we it uses tf dot nn softmax cross entropy with logistics. Uh, in professional code, we always use this built-in version instead of doing it manually. It combines both step into a single, which is a highly optimized mathematical operation, and that is more precise and less prone to the rounding errors. So that's why we do it in. So either we can do this two steps, this is the manual implementation, or else we can use this built-in function to do this thing. So I'll just run it. So this is how we get it. And yeah, so if you compare the results, this is our manual result, and this is our the calculated by our function. So this is how it looks like. I'll just run it again to confirm the, yeah. So this is done. We'll move ahead to scale dot product attention, the core mechanism behind the transformers. So basically compute attention. It takes attention QKV, and it passes it to the softmax, where Q is the query, K is the key, V is the value, and M is the optional marks for padding or casual attention that we want to do. And what it returns the attention output along with the batch sequence length and dv, and it returns the weight with batch sequence length and the sequence length. So this is how it returns the value. So how it actually works, so again, let's see how it works. So there are different steps. So first step is, we will do a matrix multiplication. Once that is done, so that is q k to the power t. So this is the first step that we will do. The second step is getting the square root of dk, so we will do that. Once we get, we will apply the mask. So if mask, we are applying the mask. And then we will do the softmax, we will pass it to the softmax function. Once that is done, we will do weighted sum of the all the values, and then we will return the output. So this is how we do it in the 5 steps, and we will return the output. So let's run it and call this function and see how we get the values. So scale dot product for attention, this is the QKV shape that we have given, this is the output shape, and this is the attention weight shape that we have got. So this is how it works. And yeah, these are some practical exercise for matrix reshape, extracting diagonals, compute trace, and then alternative of using and some. So these are some exercise that you can try. It's very easy. This one is for the batch normalization. So batch normalization, again, we have already seen in the C2, so I am skipping it as of now. and building neural network for a forward pass, and then we are done. This is the summary of the sheet, what we have done in this sheet. And if you have any doubt, you can comment on the YouTube video. I'll go through this and I'll come back. Thank you.